for dropping a paper plate through the air. Our goal was to investigate the effects of the primary resistive force or drag on the paper plate as it was falling through the air and to determine if the height would make a difference on resistive force on the object. The main point of the experiment is to understand motion through fluids or air as the forces may counteract gravity and result in terminal velocity. Examples of this can be seen when skydiving or as a ball is falling through liquid. We found that the paper plate needs a certain amount of time and distance to reach terminal velocity. Our experimental design, as we dropped the paper plate at 3 different heights, 1.5 meters, 1 meter, and 0.5 meters. Each of the drops were recorded and tracked, and the graphs were produced respectively. We used the position versus time graph, velocity versus time graph, and acceleration versus time graph to determine whether the paper plate hit terminal velocity or not.
Some of the physics involved in the presentation were resistive forces, which are forces that act against the direction of an object's motion. Drag force is one of the primary resistive forces that we looked at, which is a force that a fluid has on an object's surface. Basically, as an object moves through a fluid, it pushes on the molecules in the fluid, and due to Newton's third law, the fluid pushes back against the object's surface. The second resistive force that we looked at was viscous force. This is the fluid's resistance to the object's motion as the fluid slides along the object. Terminal velocity is a term that refers to the result of drag force and viscous force equaling the force of gravity, resulting in a net force of 0. It is the maximum velocity that an object falling or moving can reach. Depending on the situation, drag or viscous force can be more important than the other.
So we decided not to put the viscous force in our calculations because the viscous constant of air is so close to 0. It comes out to 1.81 times 10 to the negative fifth. So we just decided not to include that in our equation because it's basically irrelevant.
So for our system schema, we have the paper plate as our system, and we see that the paper plate makes contact with the air as it is traveling through it. And Earth is exerting a gravitational force on the paper plate, and the Earth is also exerting a gravitational force upon the air. And as well, the Earth and the air are making contact with each other. So this is our free body force diagram after the paper plate is released. The force of viscosity is negligible, as we explained earlier, and the force of drag is significantly higher. However, the sum of the two forces does not have as much of an impact as gravity has. And after the paper plate is released, this is before terminal velocity is reached.
These are the graphs of the 1.5 meter drop. As you can see, at around 0.6 seconds in the position versus time graph, the object reaches its terminal velocity because the graph is linear, which means that the velocity is constant, meaning there's no acceleration, which means that there's a terminal velocity. This is illustrating both the velocity versus time and acceleration versus time graphs, because in the velocity versus time graphs, it reaches a constant velocity at 0.6 seconds, and the acceleration versus time graphs, it reaches an acceleration of 0 at around 0.6 seconds. As you can see in the 1 meter drop, you cannot clearly see whether the object has reached its terminal velocity or not because it has not been observed along a great enough period of time. This is again illustrated in the 0.5 meter drop, where you can clearly see that the object has not yet reached its terminal velocity because the position graph is curved, and the velocity versus time graph never reaches a constant velocity, and the acceleration versus time graph never reaches an acceleration of 0.
So the way we calculated terminal velocity was we looked at the position versus time graph. We saw which part was linear and chose 2 points from it, the first one being 0.878 meters and the second one being 0.136 meters. We then found the amount of time between both of those points, which was 0.4 seconds. So we took the difference between the 2 points and then divided by the amount of time and got negative 1.705 meters per second. For the drag force, we set the sum of the force of drag plus the force of viscosity to the negative of the force of gravity. We already said that the force of viscosity we're assuming is 0, and we said the drag force is based on the area of the circle, which is pi r squared. So here's our equation where we ended up getting the drag coefficient to be 0.92882.
So for our conclusions, we found that mostly due to the air's low viscosity, the viscous force on the paper plate is negligible. At shorter heights, the object is prevented from reaching terminal velocity due to the lack of distance required for the resistive force to equal the force of gravity. We also see that it takes a more significant distance for the velocity to reach a large amount of magnitude, terminal velocity, for the drag force to equal the gravitational force.
Some of our possible limitations included that our video was filmed freehand and therefore was not completely straight. This could have an effect on the position that was tracked due to not being able to completely line up the X and Y axes. Tracker is not completely accurate, which also may have caused the graphs to be slightly inaccurate. The paper plate did not fall perfectly straight down, and this may be due to a breeze in the room or due to not being properly dropped completely straight. The paper plate did not fall smoothly and it shook as it fell. This is possibly due to uneven construction or the movement of air in the room, and this could have caused some of the data points to be inaccurate. We used the area of the circle in our drag equation, but the paper plate is not exactly a circle, so that could have caused some other inaccurate calculations.